Now we will talk about analytical solutions for the first order ordinary differential equations, and we will talk about several particular form of the first order ordinary differential equations and how to solve them analytically. Okay, so we have first order ODE form. And we saw that from the motivation example that the separable form, which is the most easy form to solve analytically for the first order ODEs. So the first one will be the separable equation form. And we have basically dy over dx equals fx over gy. Or you can write as gy dy equals fx dx. Then for the separable form, how we solve it, we basically just integrate both sides, right? So for the solution, analytical solution, just integral both sides. Well, we have gy dy equals integral of fx dx plus some constant. Okay, so it's the most easy one. Then the second one is a little bit complicated as compared to the separable equation form, but similar. So for certain first order ODE, which is not separable, but can be separable by the substitution using that y equals ux. Okay. And for this kind of ODE, it has an equation name called homogeneous equation. Then you may ask, what is the definition for homogeneous equations, which can indirectly use separable form? Basically, the power of each term is the same in the ODEs. And I will explain what do I mean that power of each term is the same. So we can write that ordinary differential equations using the standard form mxy dx plus nxy dy equals 0. And when we have that x can be switched by lambda x, y can be switched by lambda y, and we can rewrite this ordinary differential equations with lambda n, lambda to the n power, mxy dx plus nxy dy equals 0. If we can write in that form, which means each term will have the same power, lambda to the n, then that the solution can use first substitution, y equals ux, then the equation will be transferred to separable equation form between the u and the x. Then the third part, we just integral both sides. Okay, and we will make an example for the second part. So let's make an example. shape. Example, dy over dx equals x squared plus 3y squared over 2xy. And the first part, the first step, we will rewrite this ordinary differential equations into the standard form. So rewrite to the standard form, which is mxy dx plus nxy dy equals 0. And using this example will be x squared plus 3y squared dx minus 2xy dy equals 0. And then let's check whether this equation is homogeneous or not by using x switch by lambda x, y switch to lambda y. So we can rewrite this equation to be lambda squared x squared plus 3y squared dx minus lambda squared 2xy dy equals to 0. And you can see that we can make this power of lambda squared outside of this parenthesis equations, x squared plus 3y squared dx minus 2xy dy equals to 0. And we say this is a homogeneous equations. And actually, without doing this, you can simply just see each term, if they have the same power, then they will be the homogeneous equations. Okay. Then the next step, we will substitute y equals ux. Okay. And by doing that, we know that dy over dx will be equals to u times dx over dx will be 1 plus x du dx, right? And we also know that from the beginning, let's see. Okay. That dy over dx will be equals to x squared plus 3y squared over 2xy. That is our problem side. And that will be equals to u plus x du over dx, because dy over dx will be equals to this term. And we can substitute y equals to ux, so that we get x squared plus 3u squared x squared over 2 ux squared. And you can cancel out all the x squared term, which is 1 here. Then we get, okay, u plus x du over dx will be equals to 1 plus 3u squared over 2u. Okay? And we can make it to be a separable form. So x du over dx will be equals to 1 plus u squared over 2u. And this is a separable form, but we will just make it more clear that we make all the left term to be u, all the right term to be x, so that 2u over 1 plus u squared du will be equals to dx over x, which is a separable equation form. And you know how to solve it. We just need to integrate both sides, then we can get our solutions, right? So the first step will be integral both sides. Which is 2u over 1 plus u squared du equals dx over x. We just integrate both sides. And let z equals 1 plus u squared, then we know that dz will be equals to 2u du. So we switch the z with the u part, which is integral dz. 2u du is dz plus divided by z equals integral dx over x. So we get ln z equals ln x plus some constant. And we get z over x will be equals to e to the c, will be some constant c1, right? And we also know that z equals to 1 plus u squared will be equals to 1 plus y squared over x squared, because we do that substitution before u equals to y over x, so that we can replace the z with the y part for these equations. It's 1 plus y squared over x squared divided by x will be equals to c1. And this is called implicit solution. What is implicit solution? Is that both the function and the variables are mixed into one equations. We didn't separate them. And the explicit solutions, that is when we separate them, will be y equals c1x minus 1x squared. So that is the explicit solutions. And both are okay. And in order to get the C1, this constant, we need some boundary conditions. For example, initial boundary conditions, or boundary conditions in general. Okay.